Section 1.2, functions and their properties. When you think of functions, you might think of something that looks like this, f of x equals x squared. I like to think of functions as a machine where you put something in and something comes out. Like, for example, with the function f of x equals x squared, we could take the number 5, it goes into the machine does some work to it, and it spits out a 25. And what happens on the inside is x, the number x that you plug in, or the number you plug in, is squared. And that's the formula for it, is what happens on the inside of the machine. It pops out. So you're basically putting a number in. The function here describes what we're going to do to the number that you plug in, and then it spits out an answer. So next, we have to look at what and define what a relation is. And a relation is a set of ordered pairs and a function is a relation in which for every input value there exists one and only one output value. The input value is known as the domain, and the output value is the range of the function. So now we're going to determine whether the equations below determine y is a function of x or not. So is the output unique for each input, yes or no? So basically, we're trying to determine whether or not there's exactly one, for every input, there's exactly one output. So in this one, we can see if we solve for y, it would be y equals negative x minus 10. And if you put in a number for x, there's only going to be exactly one output. You know that's the equation of a line anyway. And so, yes, that will be a function. For this one, we have, if we tried to solve for y, y squared would equal 3x, and y would equal plus or minus the square root of 3x. So now when you plug a number in for x, there are two outputs, a positive and a negative. So this one is not a function. For this one here, when you plug a number in for x, there is only one output. There is no plus or minus, it's just y is the positive square root of x minus 5. So that one is a function. Do you remember the vertical line test? The vertical line test says that if you have the graph of a relation, like this would be a relation, if you draw vertical lines, if the vertical line only intersects the curve in one spot, then we know that it is a function, because if you had a relation like this and drew a vertical line, it intersects the graph in two places, which means for this particular x value right here, let's say that's a 5 right there. That means there's an output, a positive output, there's also a negative output. There are two different outputs. And so that's not the definition of a function. A function says that for every input, there's only exactly one output. So we have two here. So this one would not be a function, and this one would be a function because of the vertical line test. So here in this problem, we can see this one's not a function, this one is a function, and this one is a little bit more difficult. This one here, we got maybe an issue here, but no, we don't, because that's an open circle right there, so it's still only intersecting one point, and so this one is also a function. So the domain of a function is the set of all x values for which the function is defined. So we're going to now do some problems where we're going to try to figure out the domains for functions. And the things you need to watch out for, there's only two things. The first one is you can't divide by 0. And the second thing is you have to look out for taking square roots or any even root, like a fourth root of negative numbers, because you can't do that. So those are the two things that we have to look out for. So in this problem, or these set of problems, we're looking to find the domain of these functions, and then we're going to write that domain in interval notation. So again, there's only two things to look for that we just described. We can't divide by 0. Okay, that won't work. And you can't take the square root of a negative number. That's what we're going to look out for. So dividing by 0, square roots of negative numbers. So in this one, part A, on this problem, we see that we have a fraction. And so the only thing that could possibly come up here that would be a problem would be dividing by 0. And so we set the denominator equal to 0. And we get x equal to -8/5. So the domain is going to be all reals. X cannot equal -8/5. In interval notation, that would be from -infinity to -8/5, and from -8/5 to infinity. The next one, x squared minus 16 cannot be 0. And so we set that equal to 0 to find out what makes it 0, and whatever makes it 0, that can't be in the domain. So that means x squared equals 16, so x cannot equal plus or minus 4. So this one's all reals. X cannot equal plus and minus 4. That's one way to write it. In interval notation, we go -infinity to -4, -4 to 4, and 4 to infinity. Next, we have the absolute value of 3x minus 2, and there's no division, there's no radical. So this domain is all reals from -infinity to infinity. You should know what that absolute value graph looks like, and you know that that's just going to be a V-shaped graph. So that's no problem with domains there. The next one, we have a denominator. So that can't be 0. X cubed minus 4x. What makes it 0? We got to figure that out. So we're going to factor. And we get x equals 0 and x equals plus or minus 2. So that means this domain is all reals. X cannot equal 0 or plus or minus 2. In interval notation, that'll be -infinity to -2. You just go in order and go to the spots they can't equal. So -2, and then from -2 to 0, and then from 0 to 2, and then from 2 to infinity. The next problem, we have a square root now for the first time. And we know that that can't be a negative number inside, so we know that 3x minus 12 has to be greater than or equal to 0, which means 3x is greater than or equal to 12, and x is greater than or equal to 4. So we are going to write that in interval notation, and that means that x can be all numbers greater than or equal to 4, so from 4 to infinity with a bracket. And the last example on this slide is the square root of x minus 9. Again, a radical, but now that radical is also in the denominator, so we know that x minus 9 can't be negative. It has to be greater than or equal to 0, but because it's in the denominator, x minus 9 has to be greater than 0, which means x is greater than 9, but it can't equal 9. Otherwise, the denominator would be 0. So we are going to put that in interval notation, 9 to infinity. Now, the range of a function is a set of output values that come out after you plug in an input value. We want to find the range. Usually we're going to find the range. There's lots of ways you can find the range, but a lot of times we're going to find the range by graphing the function and looking for what y values are there and when there are not any y values. You here's an example of a rational function, f of x equals x squared over x minus 1. We know that we have a horizontal, the end behavior is y equals 1, so we have a horizontal asymptote at y equals 1. And we can see that there are no y values between 0 and 1. So when I say the range here, I'm going to just basically start from negative infinity and work my way up. And I can see that we have y values from negative infinity up till 0, including 0. Because when x is 0, you get 0. And then between negative 1 and 1, or between 0 and 1, excuse me, there is nothing. And including 1, there's nothing. That's an asymptote. It never does equal 1. And then from 1 to infinity. So the range will go from negative infinity to 0, including 0, and then from 1, not including 1, to infinity. And that would be the range of this function. Now let's talk about when is a function increasing or decreasing. A function is increasing on an interval if for any 2 points in the interval a positive change in x results in a positive change of f of x or y. So here's a function that is increasing on its entire domain. You can see that if you picked any 2 points, a positive change in x would result in a positive change in y. And this is going down forever and ever, but it's not going down real fast. It's not going to come back up. So the next one is a function is decreasing on any interval if for any 2 points in the interval a positive change in x results in a negative change in y. So here it would be a function that is decreasing, and we can see that if you pick any 2 points, a positive change in x will result in a negative change in y. A function is a constant on an interval if for any 2 points a positive change in x results in a 0 or no change in y, and that's a horizontal line. So we're in the next problems, we're going to find the domain and range of the following graphs, determine intervals in which the function is increasing, decreasing, or constant, and then write that in interval notation. So in the first graph here, we see that the domain, and actually there should be arrows on the end of this, so the domain would be from negative infinity to infinity. The range would be from negative infinity to infinity. It is increasing from negative infinity to infinity, and it's not decreasing at all. The next one, the domain, again, is going to be all reals. The range is all reals. It is increasing always, and it's never decreasing. This problem here, the domain is, again, this thing just keeps going forever and ever. So I guess we could change this one and put endpoints here and stop and call it the domain goes from negative 2 pi to 2 pi. I mean, we can make it do anything we want, so I'll just put endpoints there because I'm tired of writing negative infinity to infinity. The range, we have a definite range here going from negative 3 to 3 for our y values. You can see that's the lowest it goes, and that's the highest it goes, and everything in between is included. Now, the increasing, decreasing part of this is tricky because it keeps going and changes intervals. So we can see, we know this is a sine function, and each one of these tick marks would be pi over 2, pi, 3 pi over 2, and 2 pi. So we can see that for one interval it increases, that you can see it increases, would be from negative pi over 2 to positive pi over 2. but then it also increases from 3 pi over 2 up to 5 pi over 2. So we have to figure out a way that we can write that continues to repeat that situation over and over again. So what we can do, I'm going to rewrite that negative pi over 2 to pi over 2 down here. So what can we do to communicate that in writing? What if we said negative pi over 2, and the next time that occurs, where it's going to start to increase again like this, so we go like this, then it does it again. How far apart are these where it starts to increase again? Well, that's basically the period of the function, which is 2 pi. So if I say plus 2 pi k here, and then that goes to pi over 2, and put plus 2 pi k there, now what happens is if k is 0, it's going to be negative pi over 2 to pi over 2. If k is 1, then it's going to be from 3 pi over 2, because if you put a 1 in for k, you're going to add 2 pi to this negative pi over 2, and it's going to be over here at 3 pi over 2. And if you put a 1 in for k here, it's going to be up here at 5 pi over 2, because that would be pi over 2 plus 4 pi over 2, which is 5 pi over 2. So that will take care of it. For the decreasing part, it decreases from pi over 2 to 3 pi over 2. And once again, that's going to repeat itself every 2 pi. So we just put plus 2 pi k and plus 2 pi k. Well, that's usually a fairly difficult thing for kids to handle, so you might have to chew on that a little bit. The next problem looks like one we already had before, if I recall, so I'm going to skip that one. And in 5 and 6, they want you to draw your own graph where the domain is all reals and the range goes from -3 and infinity. It increases from 0 to infinity and decreases from -infinity and 0. What does that? You should almost know what that sounds like. It starts at -3 and goes up to infinity. It increases from 0 to infinity. So we could go like this. And it decreases from -infinity to 0, so we could go like this. So it kind of looks like a what? Like a parabola. It also could be like a absolute value graph. The next one, we have to go domain from -infinity to -1, and then from -1 to infinity, but there's not going to be anything at -1. So that would mean we probably have a hole in the graph. It increases from -infinity to -1, so we could just say, okay, I'm going to increase from -infinity up to -1. So let's just go, we'll go to right there. And I need to have a open circle at x equals -1. Now, I don't want to confuse you here. I'm going to do that at a little different spot because the y value is also -1, so it's the x value that has to be -1. So anyway, from -infinity to -1, it increases. But there is, and then from also 5 to 8 increases. It's decreasing from -1 to 5, so I'm just going to take this one down. Here's 5. We're going to decrease until we get to 5. And that will be colored in because the only place there was not a point going to be, and that's -1. The domain's everything else. So we're going to go decrease from -1 to 5. And then we're going to increase from 5 to 8. So we'll just come back up here till we get to 8. Then we're going to decrease again from 8 to infinity. So we're going to go back down. And that would be an example of fulfilling all of the requirements. Next, we're going to talk about the idea of continuity. Basically, the definition for a function being continuous is that if you draw the graph of it, you never pick up your pencil, okay? I turned into a straight line here on, could be a curve or a straight line. Either of those two functions would be continuous, okay? Removable or point discontinuity, you've seen that before, where we would have maybe a line, a hole in the graph. That would be removable or point discontinuity. Another example of removable point discontinuity, doesn't have to be a line. It could be, come down and have a hole like that and maybe go like that. Actually, I don't want to do that. So I'm just going to kind of come up. Okay. Jump or step discontinuity would be like the greatest integer function. Sometimes it's written intx, and that's basically a step function. Looks like this. That would be the one that's the most prevalent that you might have seen in the past. It could also be a piecewise function of some sort where you would have a graph that might go up here like this, and then here it might go like this or something like that. That would also be jump discontinuity. Infinite discontinuity is back in those days of your rational functions. Remember graphing things like this where you would have infinite discontinuity here at this a vertical asymptote. Vertical asymptotes are infinite discontinuity. Anytime you have a vertical asymptote, that's infinite discontinuity. This is kind of an extra little slide just because this is what I've been teaching in AP Calculus. This is actually the calculus definition for continuity. It says that the limit as x approaches a of f of x is equal to f of a. What a limit is basically what the function's height is getting to. So for example, if here's a function, we're going to come up here like this and then come down like this. It could be like a piecewise function. And if I said that this is a height of 4 here, and I said that this x value where that point is I didn't want to do that. Let's say that this is 1, 2, 3, for example. So let's say this point is 3, 4. Well, the limit as x approaches 3 from the left-hand side, and that's what that means, of the function, is equal to 4, because that's the height. As you get closer and closer to 3, the height of the function is 4. The limit as x approaches 3 from the right side of the function, f of x, is also equal to 4, because if I come in from the right side, as I get closer and closer to x equals 3, the y value gets closer and closer to 4. And then f of 3 does equal 4, so that means that there's no hole there, and that means that the function is continuous. So you don't have to know that this year, that's next year. Next, graph the following function, determine whether or not it has a point discontinuity at x equals 0, and if so, tell whether it's removable or non-removable. So we have to go ahead and graph this. We're going to factor out an x minus 1 over x. We know that we can cancel out the x's, and f of x will equal x minus 1, but it only equals x minus 1 if x doesn't equal 0. Because if x is equal to 0 in the original problem, if x equals 0, you would get out a 0 over 0. But in my final answer, after I simplified it, and you plug in a 0, f of 0 here equals -1. But up here, f of 0 is equal to 0 over 0, which is called indeterminate. And that does not equal 0. And it's not undefined either. It's called indeterminate. So these are not really equal all the time. They're equal. Every other value in the world that you can plug in for x, they're going to have the exact same output. So that means this is really going to graph the graph of x minus 1. That's a simpler way of writing all of this. Everywhere else, it's just going to be x minus 1. So that means that at 0, we know we can't plug in a 0. There's going to be a hole, and the hole is going to be at 0, -1. Now, we know that this graph is just going to look like the line y equals x minus 1, except at x equals 0. And that's where we have point removable discontinuity. Now you might say, well, how do we remove it? Well, you would remove it by filling in the stinking hole. And you could rewrite the function as a piecewise graph to remove the discontinuity. You could just say x squared minus x over x as long as x doesn't equal 0. But then when x does equal 0, you can say that it equals -1. And that fills in the hole, and I remove the discontinuity. But this is point removal discontinuity. That's when you have a hole in the graph.